Welcome to ADS University. My name is Will Humber, and in this session we'll be going over how to use engine models with ADS Code Leo. To begin with, we'll define what an engine model is. Engine models are utilities that are used to incorporate various source or sink terms into a Leo simulation. Examples of what can be done with engine models are modeling cavities with multiple knife edge seals, incorporating bleed flow into an axial compressor, adding flow for a level 0 cooling simulation, or using an actuator disk to model the effects of a propeller or wind turbine. In this session, we'll be covering the overall workflow of using engine models, the setup file formats, how to execute a case using an engine model, and finally, a summary of what we've done. The beginning of our procedure starts with a .agf file defining the airfoil geometry and a .wand file instructing code wand how to mesh the geometry. The result of these two is a .restart file, which will be passed to code Leo for the simulation. To incorporate the engine model, we will need to create .model files that specify the various types of simulations we'll be adding, and a .leo file to instruct code Leo to incorporate these .model files. The first format for the .model file we'll look at is for controlling the level 0 cooling flow, bleed flows, and cavity flows with knife edge seals. In the first row, the first two parameters are for controlling the level 0 cooling with respect to the inlet and outlet. These parameters can be set to one of three values: 0 for disabling level 0 cooling, 1 for enabling level 0 cooling at the inlet or outlet respectively, or some integer, enabling the level 0 cooling at an integer number of points away from the inlet or outlet. The next two lines, located here and here, will be used to establish the properties used to conduct the level 0 cooling simulation. The first parameter controls the coolant mass flow rate as a percentage of the core mass flow rate. The second parameter controls the coolant total temperature as a percentage of the core total temperature. Alternatively, the coolant total temperature can be described as a % increase relative to the core total temperature. Similarly, the total pressure can be described as a % increase or a % loss of the core total inlet total pressure. Moving back to the first row and examining the third and fourth parameters, we can see that the third parameter controls the bleed flow or cavity model for the ID platform, and the fourth parameter controls the bleed flow or cavity model for the OD platform. The ID platform is set to 1, indicating that we're using a cavity model with knife edge seals. The OD platform is set to 6, indicating that we're using a bleed model at the trailing edge. Setting the parameter to 5 would indicate a bleed model at the leading edge. Moving down 3 rows, looking at the ID platform specification, we can see that we have a knife edge seal model with 4 knife edge seals, with a clearance of 0.4 inches at a location of 10 inches, and with a rotational velocity of -1000 RPMs. In this case, looking downstream, negative rotation is defined as the components moving in the clockwise direction. Moving down 1 row, we can look at the bleed flow specifications at the OD. In this case, we're removing 0.2 pounds of mass, and we're not specifying the U, V, or W components of the velocity, nor are we specifying the total temperature, turbulent kinetic energy, or specific dissipation of the flow. If we were adding mass, we would have to specify these values. Another note is that the units used in these last two lines must be consistent with the units used to make the restart file. Moving on, we can see the definition of the actuator disk.model file. In this case, the first line defines the number of actuator disks that we'll be using, followed by the lines describing the actuator disks. The first component describes the X location, whereas the next two entries describe the minimum and maximum Z values for the actuator annulus. The fourth value describes the thrust coefficient for the actuator disk or annulus, followed by the total temperature coming from the actuator disk or annulus. Finally, in order to incorporate the engine model into the LEO simulation, a change must be made to the .leo input file. In this case, we'll be using the .model file used to specify level 0 cooling, bleed flows, or cavity models. The parameter eModel should be set to 10, and a reference to the model file name should be added at the end of the .leo file, as shown here. In order to do something similar, but use the actuator disk model, eModel should be set to 15. When running engine model simulations, it is important to ensure consistent units between the .agf and .model files. Additionally, to check your results, mass addition and subtraction rates can be found in the .mean value file. Finally, when running a restart file with more than one row, the .model file requires one set of inputs per row. In summary, engine models are an effective tool for incorporating source and sink terms into a LEO simulation. Engine models can be used for level 0 cooling, cavity models with knife edge seals, bleed flow, and actuator disk models. For more detailed information on running engine model simulations, please see the ADS technical reference. Thank you.